In this presentation, I would like to tell you about the use of air-liquid exposure models for the hazard testing of inhaled nanomaterials. Inhalation is considered an important route of exposure to nanomaterials. Because of their small size, nanomaterials can enter the deeper lungs, where they can deposit into the alveoli. Here they come in contact with the alveolar epithelial cells. In case of agglomeration, nanomaterials can also deposit in the bronchial region. From animal studies, we know that upon deposition in the respiratory tract, nanomaterials can induce inflammation. For some nanomaterials that cannot easily be cleared from the lungs, this inflammation can progress into fibrosis or even cancer. In traditional toxicology testing, cells are being cultured under submerged condition within the culture medium. And then the nanomaterials are being added to the culture medium. However, within this medium, there's a lot of proteins and salts present. This leads to the agglomeration of the nanomaterials into large clumps. And also the proteins form a corona around the materials. This really alters the characteristics of the nanomaterials. Therefore, submerged exposure is not considered a realistic exposure. Therefore, air-liquid interface exposure models are being developed. In these exposure models, the cells are being cultured at the air-liquid interface. So the liquid is only at the basolateral side, and at the apical side, the cells are being cultured at the air. Also, the nanomaterials are being exposed via the air, so there's no need to change the characteristics of the particles. There are different cell models available to test the toxicity of inhaled nanomaterials. There are models that focus on the alveolar region and also models that focus on the bronchial region to test the effects of larger agglomerates. The different cell models have different advantages and disadvantages. Here I focus on the suitability to being cultured at the air-liquid interface, as we think this is a much more realistic exposure. For a lot of cell lines, they are not able to be cultured at the air-liquid interface, for example, because they tend to overgrow or they do not remain stable and viable at the air-liquid interface. For the bronchial cells, only the Calu-3 cell line remains stable and viable up to 2 months culturing at the air-liquid interface. For the alveolar models, there is no cell line available that remains stable and viable for a longer period of time at the air-liquid interface. So for the alveolar region, you need to take primary cells to develop a lung model. There are also different ways to expose your cells. So once you have your cells cultured at the air-liquid interface, you can choose how to expose them via the air. There are more simple methods like the phytocell cloud system, in which you take a dispersion of your nanomaterial and nebulize it, and then the nanomaterials are in a cloud that settle on top of your cells. There are also more complex systems like this automated exposure system, which is a very large cabinet. In this cabinet, you have different modules in which you can put your inserts with the cells. On top of each insert, there is a trumpet. And through this trumpet, there is the airflow with the nanomaterials. At the last 2 millimeters, the nanomaterials deposit on the cells via diffusion. This is very similar to what you observe in the lungs. With this more complex system, it's possible to expose your cells for a couple of hours per day and also for multiple days in repeat. Then comes the question, what's the relevant exposure concentration and time? Usually in toxicity research, you expose at a typical time point only a single exposure, and then 24 hours later, you measure the response. With these lung models that can be cultured for days or weeks at the air-liquid interface, and the exposure systems that can also be used for repeated exposure, you can tune your own exposure. So you could choose, for example, for multiple exposures in multiple days, like 3 days, and then measure the outcome a day later, or you can do a single exposure and look at the readouts 3 days later. Or you could try to mimic, for example, an occupational exposure setting in which people can be exposed to nanomaterials for 5 days per week, 6 or 8 hours per day. And you can mimic this also in the exposure system. So you do a daily exposure for several weeks. And what's then a relevant readout to measure? This morning, Sabina has presented about the adverse outcome pathways. Here I show the AUP leading to pulmonary fibrosis. As for some nanomaterials, it's known that they can induce pulmonary fibrosis in animals. In the lung models, usually transepithelial electrical resistance is measured, the viability is monitored, and the release of inflammatory cytokines is being measured, as this fits into the AUP leading to pulmonary fibrosis. In our lab, we've been exposing the K3 bronchial epithelial cell line for 3 weeks to DQ12. DQ12 is one of these nanomaterials. It's a quartz crystalline silica that's been known to induce pulmonary fibrosis. So in our lab, we have tried to repeat this exposure via a low dose repeated exposure over 3 weeks. However, in this KLU3 cell model, we did not observe any effects of the DQ12 after 2 weeks exposure. As we did not observe any effects in the KLU3 bronchial cell model alone, after exposure to DQ12 nanomaterials, we advanced our lung model by the addition of macrophages. So now we have a co-culture model. So the KLU3 cells are cultured on the insert at the air-liquid interface, and the macrophages are added on top. The macrophages are very important in the response to nanomaterials, as they are the first line of defense. They can phagocytize the material and clear it from the lungs. Also, they play an important role in the inflammation response. Here we used either THP1 macrophages, so from a cell line, or primary macrophages from human blood. When we exposed this model for 3 days repeated to DQ12, we did observe a clear effect of the DQ12 in the cytokine response. In summary, the development of realistic lung models and a realistic exposure is a continuous optimization process. The focus is on the predictivity of the models, as the aim is to develop in vitro models that are predictive of the human situation. A discussion is about the complexity versus simplicity. On the one hand, complexity is being increased to develop as realistic models as possible, while on the other hand, complex models are more difficult to repeat in other labs, and simplicity can help the regulatory acceptance of the models. Also, robustness and transferability are of importance, as especially in a regulatory setting, lung models need to be used at different labs across the world. Taken together, it's really a group effort to optimize these lung models. I would like to thank our partners for their great collaboration, and I would like to thank you all for your attention.